on this computer. I hope I know where this records. Anyway, okay. So, let's see. On Wednesday, you're going to take the chapter 15 test, right? Or whatever this is, simple harmonic motion. But it's not going to include damping or forced oscillations, okay? So, and that we're going to finish this problem, and then I think we go into damping and forced oscillations. So yes. So we're going to do that. And then do you have a reading assignment for tomorrow? I think you have to read chapter 12 for tomorrow, yes or no? Okay, well, then let's change that. Because, let's see.
We did read 15.4.
You read 15, you read for today, right?
Yeah.
Okay, but I still think we're going to be able to start chapter 12 tomorrow. So actually, we can do this way. No, actually, I'm not going to do that. Because I want you to be able to work on that lab with the springs too. So whatever time you have left over tomorrow, we'll finish the spring lab. You have the test on Wednesday, and then Thursday and Friday, we'll do chapter 12 on statics and equilibrium. So that's a much better use of our time. Okay, so we were working on that example where we had a physical pendulum that was made of a rod and a disc. And we reviewed things like the parallel axis theorem and rotational inertia. And for part A, we figured out that the total rotational inertia was 0.205 kilogram meter squared, right?
Yes.
Okay. And then we were going to move on to part B, which says what is the distance between the pivot point and the center of mass of the pendulum. So how would I figure out where the center of mass of the pendulum was? How do I find the center of mass of anything? I could use symmetry of some kind. Okay. Is this object symmetric? Okay, so I could cut it down the middle. You mean I could like cut it like this, which would tell me that somewhere along that line is the center of mass. Okay, that's narrowing it down a bit, but I still, that only like gives me kind of one direction. I move the other direction too. Lauren?
To find like the general direction, also compare the mass of this versus the rod, and that since the disc is much heavier, like double the mass of the rod, it would be closer to that.
Okay, so Lauren says that we could compare the mass of the rod and the disc and make a prediction or a guess or an estimate that it's going to be, the center of mass will be closer to the disc because the disc has more mass. But I can't just estimate it. I need to know what it is. And Lauren hit on a really good point that the disc and the rod are separate. What if I had two pool balls that were pretty far apart? How would I find the center of mass of that? How do I find the center of mass if I have like two objects that are separated like that? Well, it's not just the average. I can't really call it the average distance. Like if I say this is x equals 0 and this is x equal x1, how do I find the center of mass? Is it that we don't remember center of mass? Okay, but the units, Fiona. M1 plus M2, good. Okay, so if I had two objects, or any number of objects, I just keep adding terms. Okay. So that's something. Where's the center of mass of the Earth? Use your words, Fiona. Guess can't see you doing this. Where is it? Where's the center of mass of the Earth? Come on, Fiona, you know where it is. Use the word. I don't have a ball. Oh, there is a ball. Well, I shouldn't touch it. I can't say. I was going to say I shouldn't use the silly ball. It's really not a fish. Where's the center of mass of this ball? This is the Earth. Where's the center of mass? In the center. Excellent. I'm not making fun. Excellent. How do I know it's in the center? Because what? Can't hear you. Yes, I couldn't hear the word. Shell theorem. Okay. Why can I use the shell theorem? Uniform composition. Okay. And it goes beyond the shell theorem. For something that has a uniform density, which is even more important than uniform composition. For something that has a uniform density, the center of mass is at the center of the object. Okay. Is the rod a uniform rod? Is the disc a uniform disc? Yeah. So what I can really say is here in the middle, well, that's, I don't quite know what I'm going to call it. We'll call it X, center of mass rod. And down here in the middle of the disc is going to be X, center of mass disc. Okay, we'll draw a better picture in a minute. Okay. So I can do that for any compound object that's made of objects that are uniform. Okay, so let's draw a better picture here. Okay, and to make it better, we'll have our object. We'll consider the pendulum when it's kind of at the bottom of its swing. Okay, so here's going to be X center of mass rod, and here's going to be X center of mass disc. So if the center of the mass of the disc is in the middle, and we'll let this be X equals 0 up here at the pivot point, because that's where I'm supposed to be measuring with respect to. Then where is the center of mass of the rod? Dagny. Okay, so, and I think we called that L. So it's L over 2, or 0.500 meters over 2, which would give me what, 0.250 meters? And where's the center of mass of the disc? Radius what? I have to measure it from where X is equal to 0. Yeah. the length of the rod plus the radius. Okay, so that's going to give me the radius was 0.100 meters, and the length of the rod is 0.500 meters. So that gives me 0.600 meters. Okay. So we good? Okay. So to find that center of mass, it's going to be the mass of the disk times x center of mass disk plus the mass of the rod times x center of mass rod all over big M plus little m. So if we plug all that stuff in, what do we get? What'd you get, Annabelle? Oh, okay. You weren't typing in on your calculator, so that's your time. Oh, no problem. There's no pressure. Fiona, what'd you get? Okay, let's see what other people got. Lauren says yes. Annabelle, did you get that? All right. So there is in fact a part C, which says calculate the period of oscillation. So this is one of the formulas that we had from Friday. So how do I find the period of a physical pendulum?
2 pi times the square root of inertia divided by mass times u times the distance between the pivot point and the center of gravity or center of mass.
Yeah. So I is going to be the moment of inertia, and h is the distance between the pivot and the center of mass, or as we'll talk about later this week, the center of gravity. So we figured out the center of mass to be 0.205. Kilogram meters squared. M there is going to be the mass of the whole thing. G is 9.8 meters per second squared. And of course, we just found H was 0.477 meters. Anybody got an answer this time?
Yeah. 2 to 3 minutes.
No. Did you multiply it by 2 pi?
Oh, yeah. Is it 1.5?
Yeah. Anybody have trouble getting that? Try again. Make sure you add the masses together. So that's like what, 0.770? Okay, excellent. All right, so the next thing that we really want to talk about is damping. Okay, so if you were paying attention last week, when I had the mass on the spring, it would go up and down, but then the amplitude would get smaller and smaller and smaller, and eventually it would just kind of come to rest. Okay, and that happens because of air resistance. It happens because of friction within the spring. It happens because of kind of the stabilization with my fingers. It would be friction between the spring and whatever was holding it. Okay, so there are a lot of reasons. And the question we want to ask ourselves is, can we quantify this damping? Can we model it? Can we understand what's going to happen? Okay. And the answer, of course, is yes. But to do that, we're going to consider an idealized case. Okay. And so we're going to have our spring attached to some mass M. And below the spring is going to be a container that has water in it. And attached to the bottom of the spring is what we call a vane, V-A-N-E. Like a weather vane. What does a weather vane do? Yeah, a weather vane tells you which way the wind is blowing, right? And so what happens is if the wind is coming from this direction, it blows along the vane and it makes it point that way. Okay, so basically a weather vane is designed to be air resistant. Okay, it's designed to get pushed with the way the air is flowing. Okay, so what happens with this vane that we have is that it's underneath the water, but every time the spring goes up and down, the water drags the vane and slows it down. But the thing is it slows it down in a predictable way, a way we can model. So we say that we model that drag force as negative BV. Where V is velocity, and B is going to be the damping constant. which is measured in kilograms per second, because it just needs to be in order to make the units work out. Okay. All right. So if we make a free body diagram for our mass here, there's going to be a spring force that points up. That's negative kx. And a damping constant that points down, that's negative BV. Now you're going to say, but there are all these negative signs. And the thing is to remember is that the drag force always has the opposite sign as the velocity. And the spring force or the elastic force always works to bring the spring back to its natural length. So those negative signs are okay because X and V are going to be positive or negative. So don't worry. Okay. So if I've drawn a free body diagram, what am I contractually obligated to do next? Newton's second law. So I've got F net equals MA. I'm going to let positive X be up, although it just kind of doesn't really matter, like I said. So when I put in all these forces, I have negative BV minus KX is going to give me MA. And like I said, remember that remember that V and X are going to be positive or negative, and that's going to affect which way everything's pointing. Okay. So I have a heck of a lot of unknowns here. Okay, you can assume that you know B, K, and M. All right, because those are things I can measure. But I have velocity, acceleration, and position. But are velocity, acceleration, and position independent? No. Okay. How are they related? Dag.
Velocity is the derivative of position and
Right. So V is dx dt, and A is dv dt, or d2x dt squared.
Sorry, I just wanted to clarify something about the constants.
Mm-hmm.
When we take away the vector symbol, do we take the magnitude of the force and then add the negative sign?
No. I'm just going to add up the forces the way they're there on the diagram. Okay. So I just added them together. And so because X and V are just in one dimension, they're either going to be positive or negative. So if my X is below, so if here's my equilibrium point, if my X is below the equilibrium point, then X is negative. So KX is going to be positive and pull it up. Okay. If my mass is moving down, if my vane is moving down, then he's going to be in that direction. And the drag force is going to point up because it always opposes the motion. So the velocity is negative, but negative V is moving up. Okay. So that's what I was saying. X and V are going to be positive or negative depending on how the mass is moving and its position and its velocity, and it'll take care of itself. No, because it's going to depend. There's like 4 different combinations the way it can work out, and this allows you to cover all of them. Okay. All right. So we can rewrite here, and I've got negative B dx dt minus kx is going to be n d2x dt squared. And then just because I can, I'm going to bring everything over to the same side. So I've got m second derivative of x plus b dx dt minus kx, and all that's going to be equal to 0. Oops. It's possible. Thank you. Tell by the look on your face that it doesn't quite work. I appreciate it. Okay. So this is a differential equation. You have solved differential equations before. Something to think about and understand, well, something to remember is that when I add these things together, they have to equal 0. Okay. So if I had, remember an x is a function of t. So don't write this down because this isn't going to be true. But if x was equal to like t squared plus 4t plus 6, say, okay, and then dx dt would be what? Plus 4, and then d2x dt squared would be 2, okay? So if I substituted all of that in over here, I'd get m times 2 plus b times 2t plus 4 plus k times t squared plus 4t plus 6. And that would have to be equal to 0. Okay? That would have to be equal to 0 for every value of t. And that can't really happen. Okay? The only way that would happen would be if t was equal to 0 and somehow we got all the constants to go away. Okay? It's only going to work for one value of t, and I need it to work for every value of t. Okay? Because I need this equation to hold all the time. So what I'm trying to tell you is that setting t up as a polynomial isn't going to work. Okay? And you will learn this if you take differential equations someday, which is sometimes called differential equations. Sometimes it's called Calc 4. It is my favorite of the calcs. Actually, Calc 3 is my favorite, but this is a close second. Right? So I'm just going to write this down again so that we have it kind of fresh. You don't necessarily have to because you didn't get anything first. And I'm going to tell you that the solution is x of t is equal to xn e to the negative bt over 2n times cosine omega prime t plus v. Negative bt over 2n. Where omega prime is equal to the square root of k over m minus b squared over 4m squared. Now, if we had much more time, which we don't, we would go through and take the derivative, the first and second derivative, substitute it into our green equation up there and see that it's equal to 0, because it is. But we don't have all the time in the world. It's a pandemic. I didn't do it last year either. Okay, but it works. Okay, I would not worry about memorizing this. I think I would probably know or note that there is this exponential decay. Okay, so that if you graph this, and let's say what we're going to graph is x of t versus t, and you've got your amplitude gets smaller and smaller and smaller. Okay. But there's kind of an envelope that follows it, and that envelope is e to the negative bt over 2n. Okay, and you get one from the bottom. So the way the amplitude decays is an exponential function. And what's really probably much more interesting to look at is the energy, okay? Because the energy is going to get smaller, right? The total energy, and losing it to friction or whatever it is. So remember that the total energy of a simple harmonic oscillator is 1/2 k xm squared. So E total for a damped oscillator, I have to remember if xm is that thing in front of the cosine function, then it's going to be xm e to the negative bt over 2m squared. Or 1/2 k xm squared e to the negative bt over m. And so again, it's going to decay following that exponential function. Questions? We do sometimes, I've seen it call this or refer to it as like zero, the initial amount of energy. All right, we good? All right, so the last thing to talk about is really forced oscillations. And I don't intend to get very far into this, much less farther than 50. Up until now, everything that we've talked about has been a free oscillation. We've pulled out the pendulum, we've pulled down the mass on the spring, and then we just let it go. And when we do that, the system follows its own, what I would call natural frequency, okay, that we've calculated. And when we talk about the frequency or the period that we calculate, it is the natural frequency or period of the system. For a pendulum, it depends on how long it is. For the mass on the spring, it depends on the spring constant and the mass that's on the spring. But this isn't always the case. So I think the best example of forced oscillations is to think about pushing somebody on a swing. Okay? So a person on a swing is effectively a pendulum. Okay? So the natural frequency of that pendulum is a function of the length of the swing. Okay? So if you pull, somebody sitting on the swing, You pull them back and let them go, they have their own frequency. If you count how long it takes for them to come back, it always takes the same amount of time for them to come back. Now that's a really good example as well of a damped simple harmonic oscillator, because you know that that amplitude decays. You know that if you don't do anything, they eventually just come to a stop in the middle. So if you're going to force your pendulum to oscillate, you can push. What happens? Well, first of all, can you push any old time you want? No. Okay. So if you just push any old time you want, what happens to that person on the swing? Gets all messed up. They don't necessarily fall off, but they kind of start twisting, and like part of it wants to go one way and part of it wants to go the other way. Basically, you get chaos in the non-technical term. Okay. So how often do you have to push the person to not have that happen? So they're up here, they go all the way out, they come all the way back, and I push. They go all the way out, they come all the way back, and I push. What is the frequency of my pushing? It's the same as the frequency of the pendulum. Okay. And then what happens to the person on the swing? What happens to their amplitude when you do that? It increases. They go higher and higher and higher. Okay. So we usually think of a, I don't know how to put it, driving frequency, maybe? Sure. We call it a driving frequency. Omega B. Okay. So when the driving frequency is equal to the natural frequency, which we might just call omega, okay? Then the amplitude increases and we achieve what is called resonance. So resonance is when the amplitude increases because the natural frequency and the driving frequency are the same. And the swing example is really the best thing to do. If you push that person every time they come up to you, they go higher and higher and higher. I don't know. It's a good question. What? There is probably an element of, well, I would look at it this way, okay? Because my next example is going to be pumping when you're on the swing. So when you pump and you're on the swing, that's one of those things that little kids have to learn. You have to pump and you have to pull and push at the right frequency, at the right time in the swing, right? And that's probably more what you're doing with gymnastics. So you are still achieving resonance and increasing your amplitude. But
basketball team picture in the chapel, the crew team will be leaving at 3:40.
But it's more about your angular, it's more about that angular frequency that you've already got going all the way around, as opposed to like the cycle of the pendulum. Okay? All right. Bye guys. Thanks. See you tomorrow.